Okay, this video we talk about the last group of matrices in application. The first one I would like to introduce is Toeplitz. Is also a name, the name of the mathematician named Toeplitz. A Toeplitz matrix is the one that a value is constant along the diagonal from left to right. Okay, so I use the color. The same color means the same value. The Toeplitz matrix doesn't have to be a square. You can have a rectangular matrix like this that form a Toeplitz structure as well. Okay. Um, Obviously, when you talk about a Toeplitz, now I'm gonna give you a second example: 2, 2, 2, 1, 1, right, and 3, 3, and 5, right? Because it's constant along the diagonal from descending a diagonal. So you can think of a Toeplitz matrix, two Toeplitz matrices. If you add them up, it's still if you have any other, this is T1, this is T2, and T2 can be any other things, right? If you add them up, it's gonna still preserve the Toeplitz structure, right? And also, if you multiply a Toeplitz structure with some alpha, the result is going to be Toeplitz. So that's why Toeplitz matrices form a subspace of Rn by n. Mhm. And if you have n by n, like in this example, n by n Toeplitz, it has only two n minus one unique value because you're gonna count this one as one unique value. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it's 2n minus one unique value. Generally, if you have a matrix A that is n by n, you're gonna have n square entries, and you're gonna reserve the n square entries in the memory. So your memory size that allocate to store a matrix A will be a quadratic function in your matrix size. But for the Toeplitz, it can be cheaper than that, right? You need only the memory space of 2n minus 1, the linear in the problem dimension. So when you add, because of the Toeplitz structure, if you add the Toeplitz, you don't have to add it element by element because you know that this is going to be unique along, I mean, this is going to be unique one. So all you need to care is that you keep the unique value in an array. For example, for in this example, you need to keep only array of two. Probably you keep 5, 3, 2, 1, 5. All right. So, and if you add them up, if you add any two Toeplitz matrices, these can be added in linear time. It can be added in linear time because you need to only operate on the two n minus one unique values. So you just need to keep the unique values and keep the index of those unique value. Okay. We also have another useful result on Toeplitz matrices. Generally, when you solve ax equals y, when a is n by n, the cost of solving linear equation is going to be about cubic time complexity. So it's O of n cubed. However, if the matrix A has a Toeplitz structure, there's a special algorithm called Levinson. These can be proved and shown to be solved in cheaper complexity is big O of n squared. Okay. Where can we see this Toeplitz structure? I'm going to show you that. The first one is from convolution system. If you have a linear system that explains the relationship in a convolution sum, this is in discrete time. So H is a linear system, U is the output, Y is the output. Okay. So and this HK, this is the impulse response. Okay. So from the convolution integrals, okay, let's review a little bit. It's gonna take h0 ut, h1 ut minus 1, all the way to the past, to the origin, to the initial u. So usually, usually an impulse response of a linear system that is stable, all right, the impulse response will converge eventually to zero as k go to infinity. This is for stable system. Okay. So what the convolution suggests you is that for okay, this is the y at time t, all right, y at time t. The coefficient of ht then multiply with u0 is going to be very small because it's going to be the tail of the impulse response, which means the importance of the oldest u, right? The u that has been seen for a long time, the importance of this when multiplied with ht is going to be very small. The ut that the input that plays more important role, that is more significant, is going to be the recent one, ut or ut minus 1. Okay. From this convolution sum, if we just write down as a linear system, linear, vector equation between y and u, you're going to see from this equation that h0 is h0 times u0. Yt is going to be a function of ut all the way back to the past, but it cannot be a function of ut plus 1, ut plus 2. So y1 is going to be a function of u0 and u1 only. Yn minus 1 is going to be a function of u0 up to time un minus 1. All right. So that's why, because if you're at time, if you are at particular time, yt, I mean, it's going to be a function of the current input and the old one. So that's why you're going to see 0 in this path area, because this will be multiplied with this, the future u, and that is not possible, right? Yt cannot be a function of the future u. So you're going to see, so in short, when you just map the convolution sum into a linear vector form, you're going to see first of all, you're going to see the lower triangular system. And if you check down the equation, you're going to see that it's going to have the Toeplitz structure. Okay, you're going to have H1 along here and so on. Okay, so this is an example of convolution sum in terms of the vector equation. A lot of times we have this question in mind that if we want to drive y into a particular point, right, what would be the sequence of u that drive our system to the target? Suppose we have the target on the left hand side. So it is going to be the system that you would like to solve a linear system where your coefficient here is Toeplitz, okay? And that can be solved efficiently when you exploit the Toeplitz structure. This is also called the finite impulse response because it seems that you truncate this into a certain term, okay? You also see the topic structure when you deal with stationary process. All right, stationary process in the wide sense, it says that the autocorrelation function only depends on the time gap between the two time points. All right. So this is called autocorrelation function for stationary process. Usually, autoregression function has a lot of mathematical properties. All right, one of them is that if you compute the quadratic form using autocorrelation function as a coefficient, that quadratic function turns out to be non-negative always. Okay, but when you lay out that quadratic function into a metric vector form, A transpose some matrix A, so that matrix actually has a Toeplitz structure because in the diagonal one is going to be autocorrelation function at leg 0. In the next one, super diagonal, it's going to be autocorrelation at lag -1, lag -2, lag -3, and so on. On the lower diagonal, I'm not sure what to call, like the one next to the diagonal one, the lower diagonal one. So this is going to be auto correlation function at lag 1, okay, at lag 1, lag 2, and so on. Okay. So if you work with a stationary process, you're gonna see Toeplitz structure in that application. Next one, we see kind of related matrices to Toeplitz. For Toeplitz is a constant along the diagonal, descending diagonal. Next one is Hankel. Hankel matrix is the one that a constant along a skew diagonal, this way, this way, this way. You see the application of Hankel matrix in the control system as well. Okay. Circulant matrix is is uh is a matrix where you cyclic shift the row above. For example, this row, right? This row, and then you shift the gray to here and push the other guy to the right. And for this one, for the third row, you shift the second row, you shift the pink one here and push the first portion aside. So um, Toeplitz structure is also a special kind of circulant property. Okay. Um, Maybe we can see some results here. A Toeplitz structure uh, can be construct in MATLAB like this. All right. Uh, okay. Okay. It's gonna take. Hold on. Take 1, 2, 3, 4 in the first column, and it's gonna take 1895 1895 in the first row, and then it's gonna take that as a base entry that they have to keep constant along the diagonal. Okay, so this is a one way to create a Toeplitz matrix. So if I trim down, for example, if I would like to get only the band of the Toeplitz matrix. Suppose I would like suppose suppose I trim T like this. Okay. I trim U. So if I trim the matrix U using the command trim the upper part. Okay, and if I trim the results on the lower part, I can use this command. So this Toeplitz structure now reduces to a band matrix. So it has only in the band along the diagonal and the super diagonal. A banded matrix also has further, a lot of properties. For example, you can derive the eigenvalues of a band matrix in a closed form. Okay. Uh, okay. This is all I want to say about this matrix. So let's continue to the last one. The last one is Nilpotent matrix. Nilpotent matrix is a matrix where some matrix power of A, some matrix power of A turn out to be entirely zero matrix for some positive integers. Let's see, for example, this one, 0, 1, 0, 0, this matrix A. If you square it, it's gonna be 0, 0, 0. So in this one, A square equals 0. Okay. For this one is called a shift matrix. Is this called a shift matrix? Because if you multiply this with x1, x2 all the way to xn, that gives you x2, x3 all the way to x xn, right? So this shift matrix, so it seems like if you multiply with the original x, you shift it down, you start the result, it seems like you start with the x2 entries. And if you suppose this is a, right? And if you apply a on a x again, that's going to be a square x. So it's going to be x3, x4, and all the way down. So it's like keep shifting, shifting, shifting. We can show that this shift matrix is also a Nilpotent matrix. A nice way of a nice property of a Nilpotent matrix is that you can show that all the eigenvalue is all one. Because now I'm going to show quickly that because a squared equals 0, right? We can show that the characteristic equation of A is just lambda to the power of n, and that is equal to 0. The way to prove is not hard. This can be exercised as well. We start with eigenvalue problem, and then if you square it, right? If you multiply a on both sides, then you get a square x equals lambda ax, and ax is lambda x, and that gives you lambda square x, right? And if you do the first, you keep doing further, you're gonna get a cubed x equals to lambda cubed x, right? And then you get to the power k, to the power of k, you're gonna get lambda kx, right? Because you can do this further until you get a to the nx, and that's gonna give you lambda to the nx. But if this is a Nilpotent matrix, there's going to be a sum power in k that gives you 0, right? That's going to be a fixed 0. That's going to be a fixed integer k that a to the k is 0. So that's why at the end, you're going to get lambda to the nx equals 0. But x is eigenvector, x is never 0, though, so that's why you get lambda to the n is 0 instead. Okay, so this is an example of a shift matrix. All right. So let's verify real quick. So I can create a shift matrix. Okay, can I? Yeah. So I'm gonna use. Okay. Oh no, not by Toeplitz command. Sorry. So let me just compute it manually. Okay. Okay, this is a cheap matrix, right? Uh, not this one. Okay, so this is a shift matrix, all right, where I shift, where the next step is I shift the second one, shift the third one, shift the third one, and shift the last one. And you can see that the eigenvalue of S is all, they're all 0. So because of the proof. So that would be all. I hope that just the introduction of these matrices will give you maybe just the starting idea. You can find more resources on these particular matrices in any matrix analysis book. I think the good one is from a good book is from Horn Matrix Analysis, this one. I always keep this as a reference when I want to look for further mathematical details. Okay, about the proof, about of some other properties, eigenvalues or transformations regarding this.